Welcome everybody to the 2021 Marine Geology and Geophysics Field Course student final presentations. Thanks for coming. I see a couple of alumni out there, and it's always good to see our longtime supporters that have been with us pretty much since the beginning, some of you. I'm Marcy Davis. I'm the course program manager and one of the TAs, and here with Sean Gulick, who's our head instructor, and instructors Chris Lowry and John Goff. Stefan Sostrup and Dan Duncan are our UTIG technical staff and TAs for the field course as well. Also joining us today are Kristen Tuchik, who is the JSG Associate Director of Corporate Relations, and Konstantino Panagopoulos, who's the UTIG Communications Specialist. He'll be monitoring the chat today. So this is our 13th annual student presentations, but it's our first virtual one. So we've got Konstantino helping us out. If you have a question, please feel free to put it in the chat, and he'll help us get questions asked and answered during the 5-minute Q&A following student presentations. You can also raise your hand and we'll call on you during that time. If we don't get to your question in that 5-minute Q&A, we're going to try to keep the ball rolling here. So just know that we'll either follow up with you in email. If you have time to stick around following all the presentations, then we're happy to just have kind of an open discussion at the end for anybody who would like to stick around. Please keep yourself muted if you're not speaking, just as a courtesy to everyone presenting today. And with that, welcome again. And I'm going to hand it over to Damian Saffer, UTIG Director, for our welcome today. Thanks.
Morning, everyone. And thanks for joining us. I think I know many of you, but not everyone. Damian Saffer, and I would like to say new director of the Institute, but it's the last year has been a strange one, as everybody knows. And just want to welcome you all for me, it's a real, it's exciting and a real pleasure to welcome everyone to these presentations, especially because of the hiatus we had last year. And so, for me, it was a little bit disappointing last year that we couldn't run the course the way that we would have liked to, and to see it back on track this year is really terrific, in particular because it's such a unique thing. It's really I know that sounds a little trite because people like to talk about things that their institutes do as being unique, but this truly is. I mean, there are basically no other programs like this where students get the kind of hands-on marine geology and geophysics experience that happens in this course. And it's not just getting out there as a kind of educational exercise, but it's actually collecting real data that are then used, for example, in recent years, they've been used as baseline data for rapid response expeditions to go back and do really important, relevant science for Texas and the Gulf Coast. And so this is, again, I think it's a really exciting and unique opportunity. And I think Sean is going to say a few words about those who make it possible from the financial side as well. But just wanted to also provide a thanks, not just to those who have provided donations and gifts, you know who you are, and Sean, I'm sure, will recognize you as well, who have made this course possible and have built it from the ground up, but also wanted to thank those who have put in Herculean efforts over the past year to make this course, not just of the past year, but especially in the past year, to make the course happen this year. And so Sean, Marcy, Dan, Chris, Jamie, Stefan, and the whole group of instructors, both in front of the scenes and behind the scenes. It's really a tremendous effort. So I'm looking forward to hearing what you all have done in the past week or so, and pretty excited about it. So welcome and thank you.
Great.
Thanks, Damian. Sean, you want to go ahead with your introduction?
Absolutely. Let me share my screen here and make this big. Okay, well, welcome everybody. So this is our schedule for the day on the right, which everybody has received. Just I'm going to do a quick slideshow, just a sort of a, if you will, a pictorial tour of our field course this year. And I want to start off with a big thank you to our sponsors, which you can see on the bottom there. So Chevron, ConocoPhillips, Hess, SEG Foundation, Shell, TGS, the Scott Petty Foundation, the Art Maxwell Graduate Fellowship in Geophysics, and of course the Quarles Vaughn Utig Field Endowment. And in addition, this year we want to thank the UT Marine Science Institute, who hosted the RV Scott Petty in its boat basin, and gave us some welcome intel about where to do some marsh cores and things like that. And then the hosts of the Dancing Dunes, which you'll see pictures of in a minute, which was the place we stayed. And then the captain and crew of the MV Miss Vivian from Sea Level Marine. That was our other boat that we used this year. And I also want to thank everybody who's going to be giving the introductions later today. So Nicholas McLean is here from Chevron. We'll introduce the first team. Andrew Quarles will introduce the second team. Cody MacDonald from Shell will introduce the third team. And Jamie Austin, who's representing the Art Maxwell Graduate Fellowship in Geophysics, will introduce the fourth team. So with that, let's do a little pictorial representation of this year's field course. So we've had a tradition since the first year in 2008 of getting all the students to sign a volleyball. So this is the 2021 MG&G Field Class Volleyball, year 13, class 13, year 14, since we had a year that we had to skip. Just a quick introduction of the teams. Here's Team 1, Kazuma and Carson. Team 2, Chris and London on the Miss Vivian's fantail, next to some of the equipment that they learned to use. And then Team 3 is Solveig and Davis, and Team 4 is Jake and Marlowe, again on the fantail of the Miss Vivian. So what we did for this year and what we do every year is we start off with lectures and labs. This year the lectures were largely virtual, and one of the labs was in person and the others were virtual. So here's just a shot of one of our virtual lectures teaching seismic reflection processing and theory, like feeding through a fire hose. So some shot gathers shown, and you can see all the students there on their cameras. And then this was one of our day that we did an in-person. So you can see everybody is in a warehouse there, and they had just done a SED lab, and we were handing out laptops for everybody to be able to do their virtual labs processing. And then this entire week they've been using those laptops to work on their data that they collected last week and create the presentations that you will see this morning. So it's really a very rapid fire, hands-on, learning through a fire hose kind of activity, where they learn all the theory, that they go out in the field, collect all the data, and then they had just 1 week to interpret all the data and build the presentations you're going to see today. So realize that in terms of the efforts involved. Okay, so once we did those first 3 days, we then went out and did our mobilization. So this is pulled up on the side of the Miss Vivian, getting all the equipment loaded onto it. You can see our air tanks going on there. You can see the discussions of how we're actually going to do all of the proper setup of our equipment. And notice everybody's safety gear, that we're always very strong on safety throughout the field course. This is setting up of our little air gun that London is doing. She took to this as one of the activities. And this was testing our little miniature air gun right here at the dockside. And then this is mobilizing the RV Scott Petty, and Scott Petty Jr. is here today representing the Scott Petty Foundation. And so this is sort of named after him and his father and his son. And it's being launched right here by the students and setting up the multi-beam there that goes onto the side of the Petty to be able to map the topography of the seafloor. And somewhere in here, I understand a screw was dropped, but you know, we won't talk about that. They're getting everything set up on the Petty. And then this is operations. So that all took place on Sunday, just not Sunday a day ago, but Sunday a week ago. And then we would take out 2 teams a day onto each of the vessels in the morning. So this is 2 of the teams out on the Miss Vivian launching our small chirp instrument over the side with a little davit. You make do with what you have in a pandemic year in terms of the boat and its capabilities, but this actually worked quite well. There it is with our little chirp in the water. And this is Chris making sure the cabling is just right for it. and bringing the chirp back on board at the end of a day. So we did sort of half to 2/3 days. And then this is us putting the seismic in the water, or rather the students and Stefan putting the seismic in the water, just hand rolling out our little 100-meter streamer that will be recording the shots from our little baby air gun. And here they're putting in the small mini bolt gun into the water, and being very careful to get everything in the water safely. So that's the air gun and the streamer being towed out behind the boat. And so we would tow both the chirp and the streamer at the same time, and the students would collect both kinds of data simultaneously. And this is them in our makeshift lab inside the boat, so collecting the chirp data through that little yellow box on the table. And then the other laptop is collecting the seismic data and doing all the navigation and everything, and the students are running all the equipment. You can see them managing the logs as well. You can see the seismic data coming in there on the right, and the chirp data coming in there on the left. Lots of discussions about what we were seeing, such as when we first saw this cool Bayhead Delta kind of just perched right in the middle of an estuary section on the chirp data. And then just a shot from one of the days of the teams and the instructors all at sea on the Vivian. And then operations on the Scott Petty would be happening simultaneously. The other two teams would head out on the Petty, and they would work with Dan and Marcy when she was out there, and Chris as the other instructor. And they would be collecting the multi-beam data and the side scan sonar data, as well as ground truthing that with grab samples. So this is them collecting little grab samples of the seafloor to see what the seafloor was made of. On the after the first 2 days of that kind of activity, they then switched operations on the Scott Petty this year and flew a drone to map how the shoreline was changing through time and do profiles with it. So photogrammetry by overlapping images along the shores using the RV Scott Petty as the base. You can kind of see a cool down shot from the drone here. And this is, of course, the shot we're all using as our background, which was quite cool, we thought. And then in addition to that, they worked with the NER, which is a local research location on Harbor Island, and right by where this lighthouse is, and they went and did marsh coring. So this is setting up a vibrocore system, which the students set up themselves, of course. And then this is actually using the little engine and that vibrating snake-looking thing to push a barrel into the marsh and collect some marsh cores. So they did this the last couple of days, and this is them, working with the folks at the lighthouse and the friendly dog that is the resident. And this is returning from a day in the field. And so what we would do is do sort of half a day or 2/3 of a day each day, and then the teams would come back to the dancing dunes for the afternoon and evening, and they would process the data that we collected during the day. So this is them doing the seismic processing of the data they just collected at sea on that day. So a real sort of collect the data, process the data in the same day, which actually turned out to be quite a benefit to understanding exactly what you're doing, despite the expression on Carson's face there. And then this is doing the multi-beam processing, ping editing, and creating the maps of the seafloor based on those data that were collected by different students here. As well as doing the SED lab processing, where they did grain size analysis, and Chris actually went and picked forams, and the students were able to take a look at the forams as well that were in those sediments. This is a shot of the sediments being dried in the oven in order to do the grain size analysis. And the cores that were collected, of course, we also had to process, so the students would split the cores and actually do an interpretation of each of the cores that was collected. So there were 2 cores, one each set of teams got to collect, and do all of the interpretation, including, of course, the Munsell color charts and the analysis of what event beds that they could see, and so on. In addition, of course, we taught them some of the maintenance and servicing of the equipment. And so here's London doing the servicing on our little mini air gun on the Saturday. And there's Stefan helping with all the parts. Every night we had the students give a nightly presentation and tell us exactly about what happened during the day. So this is Kazuma giving us a part of a presentation, and Marlowe showing us the side scan sonar data that was collected, some of the chirp data that was collected, showing a cool oyster reef that we'll hear more about in a minute. And then, of course, we had downtime. So the standard students on their phones, like all of us on our phones. Dan's standing there with a fishing pole. A little bit of relaxed time. a little bit of nap time because it was exhausting long days. And of course, we had a cornhole tournament at the end of the week that went into the night on the last night, as you can see. And the champions were Jake and Dan. So, and we had our annual crawfish boil that Stefan and I always cook up. You can see the students enjoying this. We were really pleased that everybody on this trip was vaccinated, and so we could do things like all eat together without concern. A little more of the crawfish boil, and Chris even cooked us a cobbler one night, which was great. Okay, and one other thing we did that we haven't done in past years is we did a beach excursion, talked about the profiles and the position parts of a different beach, different parts of a beach, the morphology of a beach and how they're formed. And we actually flew the drone on the beach and took some beach profiles that could be repeated in future years to watch for coastal change. So here's some shots of the drone being flown at the beach. And of course, we left our signature in the sand. And so with that, note that one person was missing from this photo. Stefan was back processing some of the data, so we photoshopped him in a rather appropriate spot up in the clouds there. And we want to just welcome everybody to Presentation Day for the 2021 MG&G Field Course. And with that, we'll be handing this over to the students to do the rest of the time. Oh, and I see Chris posted in the chat that I should say NER is the Mission Aransas National Estuarine Research Reserve, which was what we got to go to take these courses in. So I will then pass this over. The next person who's going to speak is Nicholas McLean from Chevron, who will be introducing their support of the course and Team 1 of Carson and Kazuma. So I will stop sharing there.
Yeah, great. Well, can everybody hear me okay? Yep, good. See a lot of nodding heads, which is good. So yes, so good morning, everybody. My name is Nicholas McLean, and I work at Chevron. And I must say, I'm really honored to be able to be here this morning. And Chevron has been, providing funds to this course and this program now for quite a number of years. And over the years, I've been fortunate enough to be able to participate in some of the student presentations and get to experience firsthand the impact that this kind of work has with the students. And as you all know, practical hands-on experience is critical. I mean, you get a lot of theoretical experience through academic classes and courses, but actually being able to go out into the field is something that is really unique and is really interesting because, I know it's called the Geology and Geophysics program, but there is a lot of geophysics in this program. And you think about geologists, they're always out in the field. Where are the opportunities for geophysicists to get into the field? Well, this is one of those opportunities where you can acquire some seismic data, get practical hands-on experience with bathymetry and multi-beam, things like that. So, and collecting cores and samples and doing forearm separation and things. So it's really a mixed bag of skill sets that you're acquiring in the field. When I graduated from Leeds University back in '92 in England, the only field experience I had was out in the backyard on university campus grounds, collecting, I think it was, maybe 5 or 6 channels of land data using a hammer and a plate as the source and not an air gun or anything like that. We would all take the hammer and we'd whack it down onto this plate on the ground and then record the signal with the reflections and things, and then did a little bit of processing using Promax. And Sean, you said it was like feeding through a fire hose, with the geophysics and things. And when I first got introduced to shot records and Promax, it was just overwhelming. But I've been in this kind of business now for 30 years almost. And I must say it's still overwhelming, only because I'm always trying to keep up with the new data types and the technologies that are coming into the marketplace with respect to acquisition and things like that. So it's an ever-changing field environment, and you're very fortunate to be able to get out there and acquire some of that data. The other component, of course, is it teaches you how to work as teams, right? It teaches you how to solve complex problems, work together as a team, and come up with solutions for these problems that you're trying to resolve. And it teaches you how to cooperate with other people and how to blend skill sets and lean on other people for skill sets that you may not have. So that's the other aspect of this as well, which I think these are all important things you know, field experience for somebody coming to work at Chevron is critical now. I mean, it makes a really good geologist or geophysicist having that practical hands-on experience. So kudos to you all who attend this field trip and get out there in the field and get your hands dirty and acquire the data. So I really appreciate that. And so all of these skills translate to future opportunities in the industry, whatever kind of industry, whether it's environmental or oil and gas, or whatever you decide to do. All of these skills that you're picking up today will transfer very nicely into future work opportunities. So again, I think well done to the students. I'm excited to see the presentations this morning. Like I said, it's just a great opportunity, and Chevron is proud to be a sponsor of this program. And I hope that we continue to sponsor it for many more years to come. I'm obviously going to have a lot of input and say in that, and it's yes, we're going to continue to sponsor this. This is a very important program. So with that said, I guess I'd like to introduce Carson and Kazuma. And I guess you guys are going to talk about humans and storms and climate-driven geomorphic change. Over to you.
Thank you, sir, for the introduction. Let me get my slides ready. Go. Right. Good morning, everybody. I'm Kazuma Sakamoto with Team 1 with Carson Miller, and today we'll be talking about how humans, storms, and climate drive geomorphic changes. So here's an overview of what I'll be going over today. We'll be going over the study map to show where we took our studies. And in the Lydian channel, we're going to see what is driving geomorphic change in the Lydian channel. And with the oyster reefs in Corpus Christi Bay, we're going to see if the oyster reef size influence mortality. So here's a study map. I'll be analyzing the Lydian channel in the top right corner, and Carson will be analyzing the Corpus Christi Bay with the oyster reefs in the bottom left. All right. So the Lydian Channel is a feature on the Texas Gulf Coast near Port Aransas, which is part of the Gulf Intercoastal Waterway. In 2014, the Army Corps of Engineers obtained a 20-year lease from the Texas Land Office to operate at the site. In 2020, a $97.9 million construction contract was awarded to complete the second phase of the four-phase project to deepen the channel from 47 feet to 54 feet. In August 2017, Hurricane Harvey made landfall on the shores of Rockport, right by the Lydian Channel, which has a significant impact on the geomorphology. First, we'll analyze the bed form size in the channel. Using the multi-beam bathymetry data taken from the years 2009, 2012, 2017, 2019, and 2021, we were able to see that the bed forms near the dredge channel have gone through significant changes. As seen in the graph here, in 2009-2012, the bed form sizes ranged from, on average, 0.54 to 0.58 meters in height. After Harvey in 2017, the bed form went through a reset, and they were on average 0.3 meters. In 2009, the bed forms were on average around 0.32 meters. However, on our trip in 2021, the bed forms jumped to heights of 0.72 meters. Another discovery was made by creating a surface difference model on the program IVA, where we subtracted data from the previous years to the newer years. From this data, we can very clearly see depositional and erosional pattern of the channel. During the pre-storm phase, 2009-2012, there was little deposition at the edge of the dredge channel and erosion at the dredge, as seen in the red and blue color scheme. During the post-storm phase, 2012 to 2017, the size switched where the edge of the dredge channel eroded significantly, and the dredge had significant deposition, as expected after a hurricane. During the two recovery phases, 2017-2019 and 2019-2021, there's clear indication that the channel is trying to revert back to its original depositional and environmental and erosional environment in the pre-storm phase. As you can see in these two images, it is clear that the geomorphology of the channel is trying to revert back to its past environment. Turbidity can also be tied into why this is the case. The graph here was taken from the National Estuarine Research Reserve Systems to measure the turbidity of the water around the area. Seen in the graph, pre-Harvey, the turbidity of the water is relatively low, meaning erosion rates directly correlating to the surface difference map shown before. After Harvey, the station was destroyed, so there was a period of no data as noted in the graph. However, after it was rebuilt, we can see that the turbidity of the water is significantly greater than the previous years, which indicates that the erosion rate is significantly higher post-Harvey as the channel tries to reset back to its original environment. With all this information in mind, we tie back to the shores of Harbor Island. Utilizing the drone acquired by the Bureau of Economic Geology, we were able to take photos of the shorelines to create a digital elevation model, or DEM, to analyze the distance and rate at which the shoreline is retreating. As seen in this image, there has been around 250 meters of shoreline movement in 70 years. However, in recent years, the shoreline has been retreating at a steady and slow rate. It is to note that in this image, prior to 2004, the data collected has been spread out more than recent data we have. Starting at the green line, 2004 to 2021, we can see that shoreline erosion is not as drastic. In fact, according to this graph plotting the shoreline erosion rate with the storm occurrence, where the stars indicate the erosion rate of the shoreline, you can see that there is a huge increase in erosion rate after Harvey. We'd like to say that storm affects the erosion rate of the shoreline, but because of the availability and resolution of past data, we can't get a more accurate reading to see if the storms do affect the erosion rates. To conclude this portion, the Lydian channel showed that there has been larger bedforms relative to previous years, an increase in turbidity, and over 250 meters of shoreline erosion since 1951. All this indicates that the Lydian channel is a high energy erosive environment with temporal variability in deposition and erosion during major storms such as Harvey. Overall, the deposition near the Lydian channel indicates that the ship channel will continuously have to be dredged in order to keep the geomorphology consistent in the ship channel. Now I'll pass it over to Carson.
All right, so we're going to switch gears and start talking about oyster reefs in Corpus Christi Bay for a little while. So I'm showing you a map of Corpus Christi Bay and where we have all of our data coverage, and also where we have a core with a lot of radiocarbon dates, which I'll talk about in a little bit. So for this part of the project, we're really going to focus on this upper portion of the bay where we have a high concentration of oyster reefs. Next slide. But before we do that, I want to give you a little bit of an introduction on oyster reefs and oyster reef growth. So oysters are really highly resistant to changes in sea level rise, especially if they're under their optimal conditions. So down in this model below, I'm showing you a reef growth model. So what you'll see in that gray box is the optimal growth zone, and that's where the oysters are the happiest. So they're out of the water for part of the time, but they're also submerged enough to where they're under their optimal conditions, and that's where they're thriving the most and you get your maximum growth rate. So above that optimal growth zone, you have your growth ceiling, and that's driven by mean sea level. And so then you have physiological and external stressors that are going to start regulating your oyster reef growth and health. So for that growth ceiling, what we're really talking about is desiccation. So as your oysters are out of the water more, they are not able to be as happy, and so they're not thriving quite as much. Below that optimal growth zone, you also have your critical exposure boundary, which is around mean low water, and that's where your oysters are submerged for a lot of the time. So things like salinity, predation, competition from things like barnacles and mussels, and also disease are going to be really important for controlling your growth rates. Next slide. All right, so previous years have actually looked at oyster reefs in Corpus Christi Bay. And so what they found was there were these reef die-off events that occurred in 4 different clusters. So what I'm showing you here are those 4 different clusters. So A is your first reef die-off event, B is your second, so on and so forth. And so these 4 clusters of die-off happened during periods of rapid sea level rise. But I just told you that sea level, or oysters are really good at maintaining elevation with sea level. And so what they ultimately found was that droughts are really important. So during this period, if you have drought conditions, you're going to increase your salinity in the bay, and the oysters just really aren't going to be able to survive that. And so what we really wanted to do was we wanted to look at if the oyster reef width, so if the size of the oyster reef is large enough, can that influence how long these reefs have survived? Next slide. All right, so in order to do that, we have different kinds of data and they have different spatial resolutions. So we collected both seismic and chirp data at all of our lines. And so what you'll notice, the top panel is our air gun data, which is our seismic data. Our bottom panel is our chirp data. And so one thing you might notice is that our seismic data is a lot lower resolution than our chirp data. So we can see down really deep, but you might notice that we can only see one small oyster reef in that air gun data. But if we actually zoom into our chirp data, you'll see that there's actually 5 oyster reefs there. And so we're really going to focus on the chirp data for most of this talk. Next slide. All right, so in terms of how we calculated things, we were able to get the oyster reef width just by measuring our X and Y coordinates. But all of this is kind of useless unless we can put age constraints on when the oyster reef formed and then when it died. So I mentioned that Sims et al. Core from 2008 at the beginning. And so what they did was they were able to take some radiocarbon dates and then in this 2015 paper from John, he was able to actually correlate where some of those horizons were with some of those age dates from that core. And so that's really how we're measuring how long the oyster reef survived. So we're measuring the base of the reef, the top of the reef, and the reef width, and then correlating with that with age. Next slide. All right, so the first question that we really wanted to answer was, do these larger reefs survive longer? So on the x-axis, we're showing duration of the reef survival, so how long was it alive? And then on the y-axis, we're showing the reef width. And so what this is showing is that as you increase the size of your oyster reef, it's also surviving longer. So this is great. However, you know, this could just be driven by the fact that maybe a larger reef formed earlier than a smaller reef and has just had more time to grow. So we really wanted to look at, do these larger reefs have some kind of competitive advantage over the smaller reefs in terms of being able to survive these reef die-off events? Next slide. So in order to do that, I looked at when the oyster reefs formed and then when they died. So what you'll notice, the orange dots are when the reefs formed, and they all formed around this 1,000-year period, kind of at the beginning of our time. And then the reefs died at various times. So what you'll notice is that at the bottom, around 9,000 years, we get a lot of die-off of these smaller reefs. And as we get closer to the present, you have your largest reefs dying off last. And so that might indicate that these reefs size is important in terms of surviving these reef die-off events. Next slide. Okay, but why do these larger reefs have some kind of competitive advantage? And so this is a study from North Carolina where they were looking at different patch reefs and different tidal ranges. So one thing you might notice in this B panel for the Charlotte River patch reefs is that the reef elevation is actually lower. So the optimal growth zone where the reef is growing the most has actually shifted lower in the tidal frame than these back sound patch reefs. And so one of the things that they noticed in the study, next slide, is that that Charlotte River estuary is actually a lot hotter than that back sound estuary. And so the idea here is that if you increase your temperature at the top, you're actually going to shift your oysters lower in the water column because they're just desiccating too fast. Next slide. So if we're thinking about how these reefs died, we said that they died from a drought, and then I just showed you that temperature shifts them lower in the water column. You know, why are these larger reefs surviving longer? So if we shift that optimal growth zone down, I mentioned at the beginning of this talk that below that optimal growth zone, you start getting things like salinity, predation, and competition that are really important. But we're shifting all of our oyster reefs down. So at this point, we might just be playing a numbers game. So if you have predation rates that are similar across both small and large reefs, if you have more oysters on your larger reef, you might just be able to survive longer than these smaller reefs. So ultimately, the biggest takeaway from this is that these larger reefs likely have some kind of competitive advantage over these smaller reefs that allowed them to survive longer. Next slide. So with that, we'd like to thank all of our sponsors and then all of our instructors. So John, Sean, Chris, Marcy, Dan, Stefan. I think I can speak for everyone when I say that this was a really awesome field experience. Also Becky and John, who let us stay at Dancing Dunes, the captain and crew of the Miss Vivian, and then UTNSI. And with that, we'll take any questions.
Yeah, this is Nicholas from Chevron. Oh, good job, by the way. I have a question, which I thought that was a really interesting presentation. You talk about sea level change and salinity and things like that, and the impact on the oyster beds. What about pollutants, such as agricultural pesticides and things like that, or hydrocarbons in the water? You know, we all saw and heard what happened to some of the large oyster beds offshore Louisiana after the Macondo disaster in the Gulf of Mexico. Do you know anything about that and what impact that has on the reefs?
So I know they're really good at filtering the water. So especially with things like fertilizer, they're just going to take it out of the water column. And then obviously excrete it. So that's just going to go into the sediments. In terms of like oil and stuff, I think that like clogs their gills, and so that's going to kill them.
Yeah.
So
what about CO2? Because I think when CO2 reacts with seawater, you get carbonic acid, and you know globally CO2 levels are rising. You go back 1,000 years, maybe they were quite different, perhaps. I don't know. Is there some impact there as well?
Right. So with oysters, you can kind of have two kinds. You can have either a carbon source or a carbon sink. And so it just kind of depends on where it's located. So when you create oyster shell, you're actually giving off CO2, but they can take it out of the water column and they can put it into the sediments too. So it just kind of depends on where the reef is located in terms of whether it's a source or sink.
Well, it's a very adaptable, oysters are very adaptable, right? I mean, they can survive all sorts of extremes.
Yeah.
Good, thank you.
So it looks like we've got a question from Andrew, and then also a question in the chat from David. Andrew, you want to ask yours?
Yeah, sure. Kazuma, you showed some maps or were showing erosion and deposition. Over what time periods was that deposition, and is it possible to do a budget of was there sand or sediments entering or leaving the channel?
Yes. So the periods were from 2009, 2012, 2012, 2017, 2017, 2019, and 2019, 2021. We did do some grab samples around the dredge area. However, most of it was sand from what we observed. And right where I took the topographic profile of the seabeds, we couldn't grab the data for some reason because it was just hard rock. But from what we observed, we believe it's mostly sand.
Great. Okay, David, do you want to unmute and ask your question?
Sure. My question had to do with the turbidity current, turbidity measurements from the channel, and any insight into what degree the measurements can be compared pre and post Harvey. So, you know, did they collect the data in the same place? Are they using the same instruments? If you could just tell me a little more about that.
I am not sure where they took it because I've been looking for some news articles about it, but there wasn't much information other than it was done by the NER reserves. I couldn't find much information about it.
Okay, thanks.
Chris, I think you're last up, and then we should probably move on.
I just was wondering, Kazuma, what do you think is causing these changes in bed forms in Lydia and Channel?
Well, what we wanted to say was the dredging is what's causing these bed forms to go significantly higher in 2021, because from what we observed in the multi-beam is that the dredging is way deeper than it was in 2019. So our prediction is that the dredging is causing these bed forms to rise super high, but we're not sure with it because there's not enough data to support that yet.
Thanks.
All right, Marcy, we should probably move on to the next group, yes? Okay. So let's see, the next group, Andrew, it looks like you're up to do an introduction for team 2.
Yes, hi, good morning. And my name's Andrew Quarles. I guess the whole name, Quarles Van Ufford. It's quite a mouthful. Stacy and I are really pleased to be part of the Marine Geology and Geophysics field course. We're really happy to be part of it because we both went to the Jackson School. We were both very fortunate to participate with field work. Stacy was able to do marine field work in the Antarctic and in the Caribbean, and did field work on the field in Honduras. I think field work is critical for geoscience and the geoscientist. It teaches you about the complex world and the complex self. In fact, I proposed to my wife, Stacy, at a field site where I had worked in the Solomon Islands with Paul Mann and Fred Taylor. So the reason I guess the reason why we sponsor this, it's because of, it's for love, obviously, a love of science, and you're potentially your field worker. So that, in any case, it's my real pleasure to introduce London Darce and Chris Liu. I've not had the fortune of meeting them, but I'm really looking forward to their talk. Thanks.
Hi, all. I'll go ahead and kick us off. So let me go ahead, pull the slides. Go ahead and share this. Okay. Can everyone hear me okay? Everything's good? All right, awesome. So again, as he said, my name is London Darce and my partner is Chris Liu, and we are going to be talking about various influences on Corpus Christi Bay's sediment budget in human and geologic timescales. I'm going to be taking the approach of modern industrialization and in Lydia and Channel and kind of what affects it there, as Kazuma just talked about. And then Chris will take over and talk about some buried fluvial channels beneath Corpus Christi Bay. Oh my gosh, sorry, me and Chris are sitting next to each other. We have some echo going on. Sorry. All right, firstly, as the last team finished up with their presentation, I want to do a sincere thank you to our sponsors. I transferred into geophysics my junior year, and then everything went online because of COVID. So this was a fantastic opportunity, and because I'm graduating soon, it's one that I probably won't get again. So sincere thank you to all of the sponsors that monetarily made this possible, and then the team that supported us down in Port Aransas. And everyone who is involved in that process. So when I was looking at Lydia and Channel, some project motivation that we both pulled is looking at the targeted industrialization of Harbor Island, further dredging of the Corpus Christi ship channel, and the ecologic changes that these will incur. And then later, again, Chris will talk about the mapping and interpreting the fluvial channels buried below Corpus Christi Bay. And those are vital for understanding the ancient river systems in the area and the sandbank deposits that they contain, because those are important for beach restoration and environment preservation. So I have a quick little map here showing kind of where we did various things. So I have an icon for the drone surveys that we conducted, the grab samples that we did up and down the channel, as well as around the inner bay, which is kind of the central, I guess, intersection of these four different things, the different channels, the dredge channel, and then the future targeted development in the area, and then the little lighthouse showing where we took our marsh core. So I'm really interested in kind of the environmental impacts and how the dredging of the Corpus Christi ship channel has affected the seafloor health and coastline structure. So a few methods of approach that were possible to take, we could compare grab sample data to check for coarsening over time. We could create DTMs or digital terrain maps from drone imagery to compare coastline erosion over time. We can look at the shelf, or kind of the point where the dredge meets the original channel bed, and the gathered bathymetry data, and compare that to the original location of that dredged intersection. And then also examine the bed forms over time. So these are, for my portion of the project, these are the two main tools that we used. We used a drone to image the coastlines that Dr. Chris Lowry brought for us. And we were also able to go out on the RV Scott Petty, which, as we've discussed, was equipped with multi-beam scanner, a side scanner, a grab sampling, coring tools, and a drone landing pad, which was the roof of the boat. So for that first approach, I took a close look at the grab samples and compared 2012 to 2021. This upper left map is just kind of a plot of where those grab samples were taken. I didn't label which ones were 2021 and 2012, but they're all kind of in that same area. So looking at the percent composition between the 2 years, this really doesn't conclusively say anything about coarsening, and what I was trying to look at here was winnowing. This would be a coarsening over time of the sediments, because the finer sediments are being carried away by increasing flow velocities. But as it shows in 2012, we already had a very high percent composition of sand, a little bit of clay in there, but it's mostly sand. So this, if you look at the graph that I provided from Earl 2014, it's showing that sand really needs a high flow velocity for those particles to be able to be transported. Sorry, it needs a high flow velocity for those particles to be eroded and then transported. And then it needs it to slow down for it to be deposited. So this is, it would need to, the speed in the channel would need to increase a lot for those to be eroded. And we do see bed forms moving and erosion is happening, but there's really no finer material to carry off and conclusively say that this is a good method of evaluation in this area. So the other approach that I decided to take here was to look at erosion and bed forms, as these will change over time regardless of the initial conditions of the area. So I produced, I guess it's a little hard to see there, I produced a series of profiles with vertical exaggerations of 1-to-1 here. And I looked at the slope. So as I said, it's a little difficult to see, but if you look closely, the leftmost profile is looking at a line of slope kind of along that left V of the channel, and then the rightmost profiles are showing a slope along the rightmost V of the channel. So in both of these, oh gosh, it erased the years that those were from. Oh no, it's right there. 2009, 2019, and 2021. So in 2019, because of Harvey, these definitely got messed up from what they might have, the erosional course that they might have originally taken. But we can still see that the slope of these, of this channel is increasing. And this increasing slope and this kind of furthering erosional quality is going to be important in a moment. So I want to talk about real quickly the erosion, or the dredging that is planning to take place. So I pulled this from the project proposal from the Army Corps of Engineers, and as we can see, this middle portion highlighted by the red dashed line is the existing bottom of the channel. And then this entire green portion is what they plan to dredge in the future. So any work that we're seeing here and any effects that we're seeing happen on the channel from this dredging is only going to be increased exponentially. And these effects are only going to be exponentially highlighted in the future if this dredging project goes through. And this is in the inner basin, which, as I said, is kind of the intersection of these three channels that lead out into Port Aransas Pass. So this is kind of a very, this intersectional point that I looked at these profiles at. So it will be much more sloped, much more deep, and flow velocities will increase a lot there. And that's a dolphin that we saw out there in that inner basin. So something else that I wanted to look at is what kind of, if the flow velocity has increased, how has that affected the tides and how has that affected the bed forms in that sense? So if we look at 2021 and we look at the bathymetry data that we've gathered, no matter if we're looking at the bigger bed forms or the smaller ones, we can tell that the dune direction indicates flow out of the bay solely towards Aransas Pass. The present day flow, there's no bidirectionality, there's no indication of tidal ebb and flow. Bed forms only show movement out towards the bay. However, if we look back at 2009 and even up into 2012, these ripples are symmetric with no clear flow direction, indicating that there was regular tidal ebb and flow into the channel previously, but there's not anymore. I can't tell you exactly what kind of implications that has on maybe the ecology of the area or the health of the marshes or anything, based on what kind of nutrients need to be brought back in from the bay into the channel. But it's definitely something to keep in mind going forward, is that even now we're not experiencing tidal flow in and out of Lydia Ann Channel. Water is only going out and not back in. So this is where I wanted to revisit flow speed and kind of look at these single direction dunes a little bit closer. So I believe that we can conclusively say that overall flow speed has increased. This is based on the dune height, this is based on the directionality, and there could be multiple reasons for this happening, but part of that, a hypothesis that we had out in the field is that there's an underwater waterfall due to this dredged ledge. There's a strong undercurrent that is flowing, and then when it comes to that large, as we just looked at, increasing slope drop off, the water current is increasing in speed and could keep increasing into the future. And as I just said, the flow is recently unidirectional. Here's a quick quote from Sims et al. 2006. He was talking about the characteristics of Mustang Island, which is one of the islands in this area. And he says, one of the important aggregational characteristics for the island is that there's a presence of tidal inlets for at least the last 7,500 years, or 7,500 years. So if passes like Aransas Pass have been serving as a tidal inlet for so long, and then just recently in the last less than 20 years, they're not tidal inlets anymore, they're only tidal outlets, that could have serious implications for changing the environment in this area. And then when we take kind of a zoomed out view of this area, we do see these alternating columns of different dunes, of different sized dunes. We would have one column of larger dunes with on both sides kind of smaller, deeper, smaller dunes. So this could show different possible pathways of current flow. So just to wrap up, we wanted to look at, I have some feature questions that I would like to answer just with this data that we've gathered. So things like, how does the lack of tidal cycles affect sediment loss, ecosystem development, and coastline erosion? Part of along with the dredging of the channel, a really big thing that they want to do is industrialize Harbor Island. So what kind of development in Harbor Island will influence the ecologic factors, and what can be done with the dredge spoil. So I pulled from the public notice of the project announcement. They did a very in-depth look at what kind of effects that the dredging would have, and it says the Harbor Island shoreline has been exponentially eroded. There's a ton of resources that will be affected, such as the Padre Island National Seashore, the National Park Service's Division of Sea Turtle Science. There's numerous endangered species that live there. And then they go on to say that although we understand that if there is an alternative to this, then we shouldn't do it, but there's no alternative, so we're going to do it. And that this proposed project would increase crude oil export efficiency for the nation, reducing trade deficits and fostering economic development. And the proposed project meets the project's purpose and needs. So they will not be taking these environmental factors into consideration, essentially. One thing that they did say in this notice that they would try to do is use the spoil from the dredge to build up the coastlines and to build up the area. But a study that I pulled from the Port Aransas Conservation Committee is that the sediments of spoil that they've evaluated in the past are moderately contaminated with chromium, copper, and lead. In addition, these 3 elements were detected in sufficient concentration in the various amphibians and invertebrates in the area to pose a potential threat to fish and wildlife. So essentially, we don't know what's going to happen if this dredging goes through, and it could be a really big deal in the future. So yeah, and now Chris is going to take over and talk about the Corpus Christi Bay.
Okay. Okay. Oh, I'm good.
You're good.
Okay, so now we zoom out. We look at, we wonder the Nueces River entering this Corpus Christi Bay, and what would be the drowned Paleo Nueces River like, buried underneath the bay. And then we get on the boat, we use chirp data, and we use chirp and multi-channel seismic to map the near seafloor surface using chirp and the deeper using the multi-channel seismic. This is the bay. These are the lines we collect from this year and previous years. Now I'm going to show an example image collected from chirp. So chirp shows really high resolution. It's a single source, single receiver, zero offset data, has high resolution of the near surface or near seafloor. And now a map, the black line is the seafloor, and the green line are mapped the wall of the inset valley. The white line is the top of the fluvial deposit. It's the last visible but very clear surface we can map. But it only go up to 35 millisecond to 45 millisecond. So then we use multi-channel seismic to map the bottom of the fluvial deposit. And then we generate a map. So these are the top of the fluvial deposit. So the yellow and green are the topographic low, and then the red and brown are topographic high. The next is the base of the fluvial deposit, and the blue is topographic low and then the high. Then we subtract the 2 surfaces, we get the thickness distribution of the fluvial deposit. And it shows that as it goes downstream, so it's the radius of the curvature for the meandering increase downstream, and also the thickness of the deposit. And now we compare this, we put thickness, top and bottom, and we see this striking similarity between the buried fluid deposit and the Nueces River physiology just upstream of the backwater zone. So both of which shows that in downstream, it increases the curvature of the radius for the meandering and also probably the thickening of the deposit. So now we wonder, what should we expect with sea level rising, like just by 1 meter? So we would expect to see the backwater zone and also the bay, it retreat further upstream. And in the area that is upstream of the future backwater zone, we're expecting to see a more expansion of the flood zone and also a more frequent flooding. And now we show the example of the external forces that impact landscape from the human time scale and the geological time scale. And now we want to talk about, so this really makes us to think about the predictive landscape modeling that is crucial for resilience-oriented restoration and proactive intervention. So the challenge in Texas coast is the coupled system are subject to a wide range of external forces. For instance, on top, the energy input, the high energy input would include things like hurricane, river discharge, and tide, and human energy input like cargo ships, channel dredging, construction. And also, we have to think about ecological feedback. For instance, the distribution of the mangroves and seagrass, how that is going to change the carbonate accumulation and accumulation of organic matters that change the rigidity of the substrate. That probably going to feed back to the distribution of the oyster reefs. And also is the vegetation distribution, how that feed back to the linear flow response of the hair bass, and how that response affecting the local deposition and erosion of materials. And also, I think this class has been going to different sites and is the opportunity to to test the model and test its validation potential at multiple sites to help detect set specific mechanism and to improve the confidence of using landscape modeling to prescribe resilience-oriented policies. That's the end of our talk. I would like to thank you all, thank all the sponsors for your continued support, and for our 6 amazing instructors. And this has been the best educational experience I ever had. Thank you.
Thanks,
So
team
yeah,
two.
we'll finish it up and open the floor for questions. Here's my citations that I used throughout my presentation. And yeah, if y'all have any questions.
There's a question in the chat from Cody MacDonald. Cody, do you want to take it away?
Sure. Can you guys hear me?
Yep.
Hey, London. Yeah, great presentation, guys. I was just curious, since it's a connected system, you said recently that this was an outlet only essentially, and you're observing increased flow with dredging. But what about the inlet? Where's the water coming in, I guess, and is there a similar increased flow, or you can kind of use it I guess as a baseline for is it dredged? I don't know. I might have missed that part, but what's kind of happening on the whole system and not just kind of within the channel right there?
Yeah, definitely. So I know that there is other tidal inlets up and down the island that Port Aransas Pass goes through. I don't really have an idea of the full system right now because I didn't really look at that and we had a week to look at our data. But in the future, that is definitely something to look at, because while most of this water that is flowing through Port Aransas Pass, a lot of it is coming from, as Chris was talking about, the Nueces River and the other river systems. It is definitely interesting to see where other tidal inlets are, where the ocean water versus the river water is flowing through the channel. And I think something else that would be interesting is like a salinity study over time to see if the lack of tidal inlet flow versus outlet flow there has affected such factors as salinity. That is a good point. I would like to look at that more.
Yeah, absolutely. And if you looked at or had an estimate of kind of the outlet of the river too, compared to if that can overpower the tidal response, for example.
Any other questions for team 2?
Yeah, I had a question for London. The unilateral, I don't know, what's asymmetric or unilateral flow noted by the dunes, is that caused by the dredging? It's just the dunes are trying to fill in the dredged canal?
So from my understanding, the dunes are an indicator of current flow. You can look at the directionality of them and make assumptions on flow speed, current direction, and the sediments that are making them up. So while, yeah, basically we're just looking at the direction of them. And as, sorry, I already stopped sharing my screen, but as one of the pictures that we looked at, it was showing the dunes with a very clear Stoss and lee side. So we have our up and our sharp down and then slow up and sharp down. That's indicating that the flow is going one way. If these dunes are more symmetric and they look almost like little waves on the ocean floor, we can tell that the current is going both ways. And we had those symmetric dunes as recently as 2012. As we move into the later years, such as 2019 and 2021, if we examine the exact same area, we see that all of the dunes are moving in the same direction. And this could be, as I talked about, this could definitely be an effect of dredging, because the water, there's just an increased water flow because of that underwater waterfall that I discussed, and kind of that ledge that it's caused, and the current flow moving along the ocean floor.
Thank you.
Yeah.
we should probably move on to team 3, I think. That's Cody MacDonald will be introducing.
Hey guys, I'm Cody MacDonald. I'm a geoscientist with Shell. I do deep water exploration. I have been recruiting geoscientists and physics majors for the past 4 or 5 years or so. Spent a little bit of time with UT, but I'm new to this program, so really cool to see the presentations and what's come of it. And it kind of repeat a lot of what the other sponsors have said. To get the field experience is absolutely critical, and there's a lot of kind of non-tangible things you can get from it too. That it's awesome to see you guys are continuing it. So I'm really looking forward to the next presentation. So the next presentation is by Solveig Schilling and Davis Hagemeier. And sorry if I said that wrong, guys. And the title of their talk is Multi-Temporal Perspective on Evolution of the Aransas Bay Area. So take it away, guys.
All right, sorry about that. Okay, thank you for that introduction. So yeah, this project is going to be looking at the multi-temporal perspective on the evolution of the Aransas Bay area in Aransas Bay, Texas. And this talk is going to be focusing on 2 very different topics within this Aransas Bay to gain an understanding of change in this area. So my portion of the talk is going to be focusing on the symmetry in the Lydia and channel bed forms using primarily sedimentology and multi-beam data on a very short time scale, focused on the last few decades, whereas Davis, who we're going to hear from next, will be focusing on the geophysical and seismic data from hundreds of thousands of years ago in this Aransas Bay area. And together, we're going to be able to piece together the history of the Aransas Bay. So first off, let's dive into some background and put some place to where we are. So like I said, I'll be focusing on the Lydia and channel. And this Lydia and channel is a feature on the Texas Gulf Coast and is part of Port Aransas and is situated between the Harbor Island and the barrier island San Jose. And as part of the 2021 edition of the Marine Geology and Geophysics course, we surveyed this area aboard the RV Scott Petty, pictured here. And we used multi-beam bathymetric and side scan data to emit and receive sound waves that we were able to translate into depth. So we received data that looked something like this picture right here. And after we received this data, we had to correct for error. So things like dolphins, this is a dolphin I saw off the side of the boat. They created a lot of noise in the data, so we had to go through and correct for that. But once we completed that and did our corrections, it was really striking to see the level of detail of bed forms. And since this course has been taking bed form images for a long time, I thought it'd be cool to look back in the records and compare and see how the bed forms have been changing over the previous years. So here you can see some bed forms from 2009. And I believe this is the first year the Marine Geology course collected bed form data. And you can see here that the bed forms are appearing to be really symmetrical and really uniform. And using the measuring tool on the software, I was able to calculate the period of the bed forms, and they're about 10 meters. And again, they appear so symmetrical and very, very uniform. And here's some data from 2012. And we're seeing another example of bed forms. And again, these are appearing to be pretty symmetrical, and they have a similar period of about 10 meters. And then things look a little different starting in 2019. So I think these bed forms appear to be more asymmetrical, and they also have a much shorter period. And same with 2021. 2021 looks really weird. These are even more asymmetrical. I calculated a period of 16 meters, which is significantly higher than the last ones. So then that brings me to the question of what's going on? Why are the bed forms changing? So I tried to look at precipitation in the area, climate, thought maybe I could say that this is causing bed forms to change, but I was actually kind of surprised at how little precipitation and how little climate was changing in this area. So I feel like it probably wasn't due directly to precipitation or temperature change. It should be noted, and other presentations have said this, but 2017 Hurricane Harvey did hit. So in order to figure out more about what's going on, I began to look at grab samples. And yeah, so while we were on the Lydia Ann channel, we took several grab samples. And grab samples are able to tell us sedimentology at a very specific location. They've also been taken during previous cruises for this class. And so I was able to compare grain sizes throughout this record. And then these are the locations from the different years. So I plotted up a cross plot of this data to visualize how grain size has changed. And I noticed that the earlier years, so like 2019 or 2009, 2012 were plotting as predominantly gravel and coarser, whereas the newer data was plotting as much finer sediments. So then I wanted to figure out, okay, what's causing sediments to change? So I wanted to look at if erosion was playing a role in this change. So I went back into the software and created what are called difference maps. And these are essentially subtracting sedimentation from one year to next so that you can see where things are depositing or where erosion is taking place. So this is the first difference map I created, and we're looking at the difference between the years 2009 and 2012. And you can see that there's some deposition, some erosion, but it's kind of pretty white. So not a whole lot going on here. Between 2012 and 2017, there is significant amount of deposition. And again, 2017 to 2019, more deposition. And then 2019 to 2021, there's erosion kind of on the edges and then deposition throughout the middle. And then this is a difference map between 2009 and 2021. You can see a lot of stuff is being deposited. So to try to figure out where erosion could be coming from, I looked at some satellite images from Google Earth, and I made a GIF. And you can kind of see that the channel, like the Lydia Ann area, appears to be shrinking, which I thought was interesting because you can kind of see erosion. Also, when we were out in the field, we took a core, and we took this core from Harbor Island, which I'm hoping you guys can all see my mouse, but it's kind of this area here. And when we looked at the core, we saw that it was primarily silt, which is pretty fine grained in the top. And previous grab samples taken from the San Jose area showed that the island is primarily like fine grained sand. And it's also a barrier island, so it's very vulnerable to having huge losses of sand during major storms. So the fact that the Lydia Ann Channel is sectioned between two very fine-grained areas that we know are eroding based off those difference maps in the satellite images, it could lead to the conclusion that the areas eroding on the edges could be dumping finer grain sediments into the Lydia Ann Channel. And this could be causing bed form to become more asymmetrical if there are smaller grain sizes. And also Hurricane Harvey occurring in 2017 could potentially have transported a ton of fine sediment into the Lydia Ann Channel. So now we're going to hear from Davis, who will be talking about Port Aransas on a longer time scale. So I will stop sharing my screen.
Okay, I don't know if you can see my screen just fine. And so what I'll be looking at is the paleo river channels that we can see under the surface of Aransas Bay. And so over the last roughly million years, the planet has been dominated by glaciations that occur roughly every 100,000 years. And so through the use of the multi-channel seismic and the CHIRP data, we've been able to recognize each of the last 5 events through this. So whenever each of the glaciation occurs, the sea level drops drastically, which allows for the river channels to extend much farther out into what is now the Gulf of Mexico. And so when they do that, they erode away their valleys, which leaves a definitive mark in the seismic record. And so if we can identify these horizons, we're able to sort of map the orientation and location of these rivers used to flow. And so here's the area that we're looking at. And so we can see Capano Bay, Aransas Bay, and the Gulf of Mexico. And in red are all of the multi-channel seismic lines that I will be looking at. And we can see offshore in the Gulf, we don't have a very dense array of lines, which will kind of come into play. Some of the maps that the software makes tries to interpret data in areas that we don't have any data, but I'll try to point out when this happens so some of the figures are easy to see. And so I'll start with the oldest one, as some of the older ones are more straightforward to look at. And so on the upper left, we can see the image of the seismic line after being processed. And so the blue line that's going across is where I believe the bottom of the valley is. And so we can identify it because it's a relatively strong reflector, but it also cuts through all of the reflectors that are below it and truncates them. And so that represents the erosional surface that would have occurred as the river was flowing through. And then just above it, you can see smaller channels from where the actual river itself was flowing and depositing. And then on the bottom left, we can see a figure that represents the sea level through time. And in black box, we can see area of time that is captured in valley when it was eroded away to when it began depositing. And so the image that we see over on the right is an isopac or thickness map of the valley. And so we can fairly clearly see the pink and purple, which represent the parts of the valley. And we can fairly easily recognize that a more or less east to west or west to east orientation of the valley. And we will see in other valleys, we start to see similar orientations, as on this one, it does have a bend to it, but towards the top, it still retains the same west to east orientation. And then in the upper left, we can again see the location of where the valley is in the seismic line. And then the bottom, we can see the time period, which is about 100,000 years before the valley that we just looked. And so the 3 is interesting, as I believe this is the valley that most really shows that we have missed any valleys, because we see in the sea level curve that the glaciation that occurred at this time period was significantly different than the ones and lacked the same strength that the other ones did. And so I believe that reflects in the thickness, as we see a much shallower valley, which I believe represents that river didn't have as much time to erode away and wasn't able to erode as deeply into the area. And also as the sea level was rising, it didn't have as much of an area to deposit sediment in, which results in a much shallower valley. But again, on this one, we can still more or less see the east to west orientation of the valley. And then valley 2, we see a slightly different orientation, but it's still more or less east to west. This one's more northwest to southeast, but it doesn't change drastically from any of the other valleys. But the interesting thing that we find is when we look at the most recent valley, valley 1, we can see it's drastically different in orientation, and we see there appears to be 2 distinct channels in the onshore Bay area and one offshore. And so I believe we can explain some of the orientations of why it's changed. So on the right, we can see the orientation of Valley 4 that I showed earlier, which again was the west to east orientation. And over on the left, a picture of what the modern day area looks like. And so we can see that Valley 4 and many of the other valleys appear to have an orientation that ports almost directly through where Rockport is and through the area that is the Inglehead Barrier. But if we look through some of the literature, including where I get this image from, we find out that the Ingleside Barrier is a member of the Beaumont Formation, which deposited in the late Pleistocene, which means that it was deposited sometime in between when Valley 2 and Valley 1 formed. And we can see here is more or less what the orientation is of the most recent valley, which shows that it flows almost completely around where the Ingleside barrier is. And so it most likely flows in this direction because after Ingleside barrier was deposited, it became a region of higher topography that the river want to flow through, as rivers stick to areas of lowest elevation and areas of least resistance. So I believe that would have caused there to divert the orientation that had bore and flow around this, resulting in what is a almost 90-degree difference in the orientation of the valley. And so we also can see in the data is that there appears to be two distinctly different channels, which is something that we were not able to see in many of the other, or any of the other paleo valleys that we saw. But if we look at some of the chirp data that we have, and on the right is an example of one of the horizons was picked to represent the top of the valley. And so we were able to look at the difference between the seafloor and the top of the valley and get sort of a depth below the surface as to where these valleys occurred. And so it's somewhat difficult to tell because the colors are different for each of the maps on shore or on the map. But the offshore section, the top of the fluvial, is significantly deeper than the area in Aransas Bay. And I believe that shows us that the area offshore was most likely where the originally flowed through, but at a certain point during this time, something occurred farther up the river channel that caused it to divert flow and flow through the new river channel that we can see at a much higher or a much lower depth, higher towards the surface depth in modern Aransas Bay. And so in conclusion, we can see that from around 500,000 to 100,000 years ago, we can see that the valleys had a more or less similar orientation and the direction that they flowed in, and thicknesses that reflected the strength of the glaciation events that occurred at that time. But around 100,000 years ago, or sometime more recent than that, the river was forced to drastically change its course from where it occurred before, as a result of the emergence of the Ingleside barrier, which caused the river to flow in what is more or less the orientation of modern Aransas Bay. And so we would like to thank all of the sponsors that contributed to allow us to have the fantastic experience of being able to go out and do field work and get our hands dirty and actually acquire this data and give us a lot of different experiences that most students are lucky enough to have. And so we really appreciate everything everyone has done to give us opportunity. And I think now we can take questions.
Yeah, Davis, great presentation, both you guys. It's really hard interpreting seismic data with that few lines and that data integrity. So hats off to you. With that, some of the channel interpretations you had, there's kind of a bust in the data, kind of right on both sides of where the channels are. Do you have any kind of alternate interpretations on, instead of a 2-channel model for, I don't remember what depth it was, that, maybe those two could connect up there, or kind of what are your alternate interpretations here?
As far as Valley 1, as for having 2 different channels, I believe it's possible, and I believe another interpretation could be that it was 2 separate river systems at that time that flowed in the area, and maybe they met farther down and became a larger system that then formed, because the other kind of alternative to that would be there was a system that broke apart, but I don't think that makes a lot of sense as far, because rivers don't frequently break up into other large systems. And so I believe that if it wasn't the river that flowed in the different times, another likely interpretation could be that it was 2 separate systems that then combined farther downflow and became the system.
Gotcha. Thank you.
Great. Other questions?
I have a question for Davis. and for Solveig. But it's mostly to do with the channels, I guess. So for Davis, sea levels going up and down and up and down, and it itself isn't really driving net accumulation of sediment. So there must be, that's some subsidence going on. And I'm wondering if the amount of subsidence that we is reported for that area, the long-term geologic subsidence, is consistent with the thickness of the whole package that you're interpreting. Because the package looks pretty thick, and I'm not sure that the subsidence is consistent with that, but I'm not sure. So that's my question.
I don't believe the substance is completely responsible for the thickness of it. I believe that a lot of the thickness and the changes from that, a lot of it comes from possibly changes in the river system throughout time, because the river's not going to flow with the same strength, and it's not going to deposit sediment same rate throughout time. So I believe a lot of it might change with the strength of the river being stronger or weaker, and so it would change the deposition that we might see in the valleys. And so I think that is also one thing, and the strength of the river also could lead to deeper valleys, as in it's able to more erode away. And subsidence also might have quite to do with the change of deposition that occurs, because as the sea level drops, or the area falls lower below level from subsidence, it's going to be able to receive more deposition as a result of it. I believe a lot of differences in thickness more likely come from changes in the river system that flowed through the valley.
Great. Any other questions? So I'll ask a quick one. Solveig, you had a slightly different interpretation than the other two groups about the reason for the unidirectional bed forms. I'm just curious, having now heard their presentations, and thinking about whether the dredging matters or not, or in this case, it has to do with the grain size evolution as you were prescribing. Do you have any additional thoughts beyond your presentation on which way it might be?
I think I'd like to look into more into the dredging aspect, because I really didn't look into that when I was putting together my presentation. And I think that would be a very key piece in changing what my interpretation would be.
Well, having said that, yours is a very interesting interpretation that the grain size story post-storm matters, which is, don't discount your own ideas here by any means. Any other questions? Okay, then let's move on to Team 4. Jamie Austin will be leading us off.
Yeah, hi, everybody. It's a pleasure and a privilege to be part of this today. It's my job to introduce Team 4, and I will in a minute, but I want to give everybody a bit of background on the Arthur E. Maxwell, what is now called the Memorial Fund. It was the Graduate Fellowship in Geophysics, but we decided some years ago that we would make the proceeds of this endowment, which I started in the early 2000s, contributory to the field course. And so we thought it would be appropriate to change it to the Memorial Fund. Art Maxwell was director of the Institute from 1982 to 1984. He had a very, very distinguished career in the Office of Naval Research. He was president of AGU. He was the second in command at Woods Hole Oceanographic Institution for about 15 years. And that's when I first met Art, when I was a graduate student there at MIT Woods Hole in the 70s. He was a wonderful guy. He died a couple of years ago at age 94, but he was very, very responsible for bringing the Institute, which was the Galveston Geophysics Laboratory when I joined it in 1979 on the coast, and bring it up to the main campus in 1982. And then it really began to take off, and it is what it is today, largely because Art brought the Institute up from the coast. I want to just take a note and say, I want to echo what everybody says about expeditionary science. That's what the Institute has done, continues to do. I've spent 4 years of my life on research cruises around the world. And in case you think your instructors just work on the Texas coast, I've worked with Sean, John, and Stefan off the East Coast. I've worked with John, Marcy, and Stefan in the Eastern Mediterranean off the coast of Israel. I've worked with Stefan everywhere, in the Indian Ocean, looking at the tsunami, the big tsunami, 2005. I've been with Stefan in the Antarctic. I've been with Stefan all over the place. And so it's a wonderful way to have a career. And I encourage you all to stay in expeditionary something, whether it's in geoscience or something else. I'm in my 43rd year here now, and it's exciting to me now. I walk down a dock and want to get on every ship I see. So it's a great thing to do. I applaud your efforts. And now with that, I'm going to introduce Team 4, and it's Marlowe Bueler and Jake Burstein, and the title of their presentation is Barrier Island Change Observed on Millennial and Yearly Timescales. Team 4.
Thank you so much, Jamie. We'll get started here in a second. Welcome everyone to the final presentation of the day. I'm Jake, and Marlowe will be with me, and we'll be talking about barrier island change observed through millennial and yearly timescales. Next slide. First off, a thank you to all of our sponsors for this amazing field experience. I, for one, would also like to thank you guys for a way to get away from all this pandemic and have a real field experience. I think it's been about 2.5 years since I've been on a boat, and it was really special, and also to work with folks. And also a special thank you to UT MSI, Becky and John Fail at the Dancing Dunes, and the crew of the Miss Vivian. So without further ado, we'll get started here. A little bit of background on barrier island change through time. So the main driver of change has always been thought to be this episodic sea level rise throughout the Holocene about 12,000 years ago. And so we have these episodic rises and spikes in sea level driving change. In the top right corner, you can see this diagram of this fluvial valley that was carved out when sea level is super low, and then back steps as sea level rises episodically to create these barrier island systems. However, other factors like climate and storms can also play pivotal roles to the barrier island system on both millennial and yearly timescales. And of course, it is pertinent to understand how these processes work in order to adapt our coastlines to ongoing anthropogenic change. Next slide. Again, so we'll be exploring 2 different areas today. One in Corpus Christi Bay, we'll be exploring the estuarine depositional history on millennial timescales. And then we'll move on to the Lydia Ann Channel, looking at erosive pits and depositional bed forms changing on yearly timescales. So within Corpus Christi Bay, we'll be looking at around 250 kilometers of chirp lines. Within the bay, we'll be using field data from 2009, 2012, 2019, and this year, 2021. We'll also be tying this seismic to a core from Sims et al. 2008 that the first group went over earlier today. And so here's just a quick look at the Corpus Christi estuarine stratigraphy. What we've done is mapped 4 different horizons. So the first horizon within these terp sections is H1, which is going to be the seafloor. And then we'll move on to H2, which is going to be the base of our estuarine deposits, which corresponds to the top of the fluvial valley, when these bay sediments flooded these valleys, forming modern Corpus Christi Bay. We then have these interesting reflectors on the left-hand side that are above the fluvial sediments that we've mapped as H3 as the top of this Bayhead Delta sequence, and H4 the base of this Bayhead Delta sequence. Next slide, please. So looking at the estuarine fill, what you're seeing before you are 2 different structure maps and an isopac map on the right, which is just thickness. And again, this is in 2-way travel time. As you can see, H1 is mostly this flat-lying reflector, this seafloor reflector that significantly increases depth near the navigation channel. H2 is reflecting this channelized feature that is actually decreasing depth and flattening out at the edge of the underlying fluvial valley that Chris was talking about earlier. And we then take a thickness map between these 2 reflectors, H2 minus H1, giving us a complete estuarine thickness of our section, where we have greatest thickness within the underlying fluvial valley, which thins over the valley edges. And this is largely expected within our sequence. Next slide. We also want to talk about this relatively young Bayhead Delta. So the top slide, this is on the left, you'll see this full waveform data next to an envelope data. And both are displaying these incline reflectors. And what you see in the blue is that incline reflector mapped between these two orthogonal lines. Going down to the big picture on the second, we can see that this feature, this H3 to H4, is prograding over this southwest fluvial terrace. We can then tie our seismic and these surfaces to the core from 2008. We can see this relatively salmon color, or H2 reflector, corresponds to this flooding surface that they have dated around 9.6 thousand years ago. We can then map two other flooding surfaces that they've mapped and dated. Flooding surface 3 at 4.8 thousand years ago, that largely corresponds with this downlapping surface of our Bayhead Delta sequence. And then on top of that, we had flooding surface 4 around 2.6 thousand years ago, that's corresponding to largely the depth of our Bayhead Delta. Next slide, please. And this is some structure and isopack maps of that feature. So the top, we have the top of the Bayhead Delta structure. We can see that's relatively flat to the southwest and largely dips down into the bay. The bottom of this structure shows largely the same feature, where we have these flat-lying features that dips down into the bay. But the thickness map, taking the difference between them, really shows us some interesting stratigraphy here. So what we see is that the Bayhead Delta, the thicknesses, is largely constrained to the southwest, and it thickens as it progrades beyond the underlying fluvial terrace that it's over until it terminates into the bay environment. Next slide. And so we really want to look at the progradation direction and the possible origin of this feature. What you're seeing here is a 3D cube in the top left. And we can see the bottom and the top reflectors there, but we also map the incline reflector that is intersecting them. So when we map this feature, we can see that, the next animation, please. We can see that the incline reflectors are showing this east to northeast progradation direction. And so next animation. And so again, if we think back to when this started about 4.8 thousand years ago, we can see that around this area, Sims et al. 2008 finds that the Nueces River Bayhead Delta was largely constrained to the Nueces Bay in yellow. So if we're thinking about where these incline reflectors are coming from, it's possible that it's coming from this adjacent Oso Bay River, creating this secondary Bayhead Delta and building out the shoreline during this time. And so if we want to talk about mechanisms for change, so going back to our horizons, so we know that the initial drowning of the Nueces River Valley happened around 9.6 thousand years ago, where we had these rapid sea level rise flooding the area and depositing these bay sediments. But around 4.8 thousand years ago, we see the onset of this secondary Bayhead Delta. And from Toomey et al. 1993, we can see that this corresponds to a switch to a warm and dry climate, stripping the upland soils, creating greater sediment supply for this younger Bayhead Delta. And then by 2.6 thousand years ago, these upland soils were depleted, leading to less sediment supply and largely the drowning of this secondary Bayhead Delta. So all this is to say, the main takeaway of this is that climate change could also be a factor other than sea level rise for millennial scale change to barrier island systems.
Thanks, Jake. So now I'm going to take over and transition over to the Lydia Ann Channel. So Lydia Ann Channel is located here. It is northeast of Corpus Christi Bay, and it's in between the Barrier Islands and this mainland island over here. The questions that we're going to be tackling today for Lydia Ann are going to be, how is the geomorphology of Lydia Ann Channel changing? And specifically, how have these two main things, the millimeter to meter size ripples or dunes and the large 80 to 200 meter long depressions changed in grain size, and what is cause and what is driving these bed forms to change. And we're going to be using multi-beam data from the past 12 years and the grab samples, the claw, from the past 12 years as well. So you can see here the bed forms and the depression. And this is a map from a bathymetry map from 2021 from London Darce. And the dominant influences on the channel are currents as well as tidal flows and shipping. And since the channel lies in between barrier islands and the land, they are very susceptible to ebb and flow, storm surges, and are also sensitive to changes in sediment flow. And so next, we will consider how the grain size of the bed forms in the pits have changed over the past 12 years. So 2009, you can see that in the depression, there is much more gravel than in the nearby bed forms. This makes sense because the pits can either trap coarser grains or the finer grain sediments can be eroded away and taken to the smaller bed forms and deposited there. And it could also be that both processes are occurring. In 2012, it's pretty consistent with 2009. There's a much higher percentage of coarser grains in the pits than in the bed forms. We can think of 2009 to 2012 as the natural period, meaning they are only minimally impacted by storms and they're sampled before the nearby dredging began. We can also see that there is a higher percentage of sand in the depression than in the bed forms. So the finer grain mud is more dominant in the bed forms. It is likely that the mud from the pit has deposited in the bed forms as previously stated. 2017, we can see that there has been a lot of change. We see that almost all the mud and gravel has been removed from the system. I wonder why. Hurricane Harvey has shocked the area and the bed forms and the depression have been leveled. And now we'll see exactly what happened to Lydia Ann Channel. So here is a very lovely graph showing Hurricane Harvey's impacts on the geomorphology of Lydia Ann. The bed forms have been completely leveled and the pits have been filled in. Next, we'll talk about how the channel is recovering. A quick thank you to John for this amazing graph, showing how Lydia Ann is affected by the landward surge and seaward surge overlapping, meaning the two essentially work together to move sediments both directions and flatten out the bed forms. On the depth profile above, we can see how the depressions never flattened out after Harvey. So in 2019, both bed forms and depressions are recovering sediments, but at different rates. They both have an increase in gravel and mud, but a decrease in sand, possibly shedding, getting rid of all the excess sand that is not natural for the velocities of the flow near the bottom. They seem to replace much of the sand with mud, since mud has a lower settling velocity, as I learned in Dr. Moritz's class. And in 2021, the depressions are still shallow, and we see notable influx of sand into the system, which is a very interesting change. There is gravel in both systems now, which was not the case in the 2009 to 2012 period. And now we're going to talk about why the change in grain size, or how the grain size has changed over the past 12 years. The 2009 to 2012 time period has expected ratios of coarse to fine grain sediments based on what we know of their settling velocities. 2017 has a large influx of sand from another area, possibly from coastal areas and from the storm ebb flow surges of Harvey. Because the Hurricane Harvey was spinning counterclockwise and landed northeast of the channel, it impacted the systems with new sediment and rapid erosion. Both areas had a decrease in mud, but the bed forms had a significantly large decrease in mud. Now, for a look at 2021, we would expect the systems to be recovering from Harvey and returning to their pre-hurricane ratios. However, we see that that is not the case. It is unexpected that the grain size of the pits is decreasing in gravel, increasing in sand, and decreasing in mud. The same conditions in 2017 as a result of Harvey. So what is causing these changes to the channel today? What is causing the loss of mud and increased sand? Well, I hate to beat a dead horse, but our hypothesis is dredging. Dredging began May 29th, 2019, directly to the south of the Lydia Ann Channel as seen by the yellow line on the map. They increased the depth of the channel from 47 to 54 feet and the width from 400 to 530 feet. It could have allowed the channel to be more open to erosion by the tides. According to a 2015 study done along the Dutch-German border, the title of the article being The Impact of Channel Deepening and Dredging on Estuarine Sediment Concentration by Marr in 2015. They found two profound observations. The first being that channel deepening appears to be a main factor for enhancing the transport of sediments up estuary due to increased salinity-driven estuarine circulation. And the second being sediment extraction strategies from the ports have a large impact on estuarine suspended sediment concentration. They found the main mechanism was called an increased tidal amplitude. This means that it's the increase of strength and velocity of the tides. And in the case of dredging, it is common for the flood or inland tide to be stronger, although that might not be the case here. And as a result of increased tidal amplitude, the study found that the suspended sediment concentration increased by 3 orders of magnitude after the dredging began. And it continued to increase. And this is most likely due to the fact that dredging requires constant redredging to keep the channel the way that it is.
Sorry, I was muted. Yes, so in summary, so Corpus Christi Bay was initially formed from rapid sea level rise, but climate change played a big role in providing the sediment for this younger bayhead delta. So we can see that climate change is also a factor in shaping this barrier island evolution.
And data from the past 12 years shows evidence of a change in grain size as a reaction to environmental changes like hurricanes and dredging. In 2017, Lydia Ann Channel became extremely flat, meaning many bed forms disappeared. Coarser grains and depressions and bed forms were depleted as a result of the Hurricane Harvey. The channel then went into recovery mode. The ratio of coarser to finer sediments increased in the area, but the pits did not become deeper. So the system never returned to what it was before 2017. The 2021 data tells a similar story with a different cause. It is possible the dredging has increased tidal amplification and caused a large increase in suspended sediment concentration, lowering the levels of mud in the Lydia Ann Channel. That concludes our briefing. Are there any questions we can answer?
Great, thanks guys. Questions? No questions.
I think it's interesting how we all brought up dredging and just kind of expanded on it every time.
I guess you could ask the same question. We could ask the same question of you as was asked of Solveig, because she really investigated the precipitation and all. And so, what are your thoughts about that, precipitation versus dredging?
And I'll probably say the same thing. You know, I would need to look more into it. I didn't really consider precipitation. I guess I've always considered. I guess living in Texas, never really considered precipitation as a dominant eroder, but that's definitely something we could look into.
Yeah, I think it's interesting that Solveig brought up that there isn't a lot of precipitation in the region. That would influence, this large change in the channel. I think I would definitely say that dredging is playing a large role in increasing the tidal amplitude in the area, and that would pretty much help to explain the these bed forms showing up, these pits changing over time, and the grain size changing.
Sounds like you need to do a proposal.
So what kind of measurements might we be able to seek out for the tidal amplification that you're proposing?
The study that was done along the German-Dutch border, they took water velocities and they had 4 different like sensors along the estuarine area, like near the place where it's dredging, and then like a little further away, a little further away. So definitely something that would take water velocity, and then something that would take the amount of suspended sediment, like that concentration in that area.
I definitely think that that data is available. Unfortunately, we just did not include it in our presentation.
Any other questions or comments? David, I see your camera on. I don't know if you were.
I was going to ask a question about the dredging of the tides, and specifically about the Estuarine Research Reserve data, which must have that, but the question was answered before I got to it.
So I'll ask a quick question to Jake about the interpretation of the. So you linked of the Bayhead Delta and the climate driven. You linked this back to an onshore study, right, about climate and then erodibility of the landscape, basically in terms of sediment flux. Was there a what was the basis of that study? What was the data that?
Yeah, the data they were collecting was really just Toomey was looking at the Edwards Plateau and noticed that around 8,000 years ago, the soil started to be depleted and was completely depleted by 2.6 thousand years ago. And a lot of this was summed up in Sims et al. 2008. But basically what's really important is by the middle of that, around like 4.6 thousand years ago, we had reached a climate that was this hot and dry period had culminated at 4.6 thousand years ago and then started to decrease. But they were mostly looking at the depletion of the upland soils in that time. Right.
Got it. All right. Any other questions?
Great job, everybody.
Yeah, well done. So we're now in the wrap up. So this is just sort of an open. If anybody has any follow-up questions or comments just about anybody's presentations about the course, we've got a few more minutes.
I just wanted to congratulate everyone and remind all of our visitors that most of these data were collected less than 2 weeks ago. I think it's very impressive.
Yeah, this is a really impressive amount of interpretation that goes on in a week.
In a week, yeah.
Jonathan, I see your hand up.
Yeah, sorry. Thanks, Sean. Yeah, great presentations. I'm a SAGE alum, or sorry, I'm a course alumni from, I think, 15. And yeah, such a great, way, like, not every of us, we weren't never able to make it all the time to these types of things. So it's really nice that we can view these on Zoom now and be anywhere and look at them. I actually had a question kind of in general for anyone that did any of the interpretation work with the seismic data, if they saw any faults or anything like that. I'm a structural geologist, and from this course, I actually used some of the data from this course for my thesis work and for a paper that I wrote back a couple of years ago. And some of these faults come up all the way near to the surface. So I was just kind of curious if any of you saw anything that was interesting but didn't have time to look at, or I'm always looking for some of these near surface faults in the area because it's a really interesting problem to look at.
How about it, guys? Anybody see any faults in this year's data?
I think if anybody did, Davis probably would, because he was looking deep in the section.
I was looking in Aransas Bay, and I think I looked probably deeper in the seismic lens than anyone else, but I didn't really see any faults, or at least none that I could distinguish in any of the data that I looked at. But a lot of the data fairly deep was pretty noisy, and so it was kind of hard to interpret some of the later data.
So Jonathan, I can tell you that in the Galveston area, we see a lot of faults there. Yeah.
We definitely see them in Galveston. We definitely saw them off Freeport, where your study, or in between where your study was. But I think I agree with what Davis said. And anybody in Corpus Christi Bay see any faults? No. Yeah,
I
I
want to
don't
say
think.
that I had seen a small one, but in the chirp data, but it's hard to say just from reading the chirp. We would have to look at it closer.
Yeah, but nothing like we see off Galveston. It's really a distinct difference along the Texas coast. It's really interesting.
They look small up where you guys are looking in, but they can be down as 20,000, go down really far. So that's kind of like the tip of the iceberg. But yeah, that doesn't surprise me. But I'm always, like I said, I'm always kind of interested in what kind of what the data might show in different parts of the coastline. Because yeah, just those faults can be moving. They're just creeping along as even they're not just moving in the Miocene or the Eocene or later. It's sometimes they're just still moving in some way. So yeah. Anyway, interesting problem, but I'm glad that there's a lot of other things to focus on, and you guys found a lot of cool topics to talk about today. So congrats on a good course, and yeah, good luck with everything else.
Thanks. Any other comments or questions in our last few minutes? All right, well then I want to thank everybody for coming on behalf of all the instructors and all the Jackson School team that helps us pull this together every year, everything from the fundraising to the communications to the hosting of this first time virtual effort, as well as all the logistics that go into behind the scenes at a place like UTIG to do everything like, get the boat contract handled through UT Legal. Some of these things are not small efforts by any means. And especially thanks to all the sponsors here, to Scott and to Cody representing Shell, and to Nicholas representing Chevron, and to Andrew and Stacy, and then Jamie leading the team of people who represent the Art Maxwell Geophysics Fellowship. So thank you all. And mostly thank you to all of the students for the real efforts you guys put in here. And hopefully we will get to see each other later socially. And as a final thing, if everybody could bring their laptops back to us so we can return them to Mark Wiederspan at the Institute to take care of them. And anyway, thanks everybody for attending. This was really great.